Hey guys, welcome to Cougar Chem Tutoring. I'm Austin. I'll be running through part 1 of problem set 5, light. Alright, explain what a photon is. A photon is literally a quanta of light. Quanta meaning a unit of light, okay? A unit of light. You may also be heard it called a packet of light or a packet of, I'll say, radiant energy. Radiant energy. Radiant just refers to light, okay? Radiant energy, okay? And the way we actually quantify this is by the equation E is equal to h nu. Okay, E being energy. This is what we call Planck's constant, which you'll see on your equation sheet, and this is frequency. So frequency. This Greek letter here is called nu. It looks like this right here. Okay, it's just the value or the letter that we use to represent frequency. A lot of times you'll actually see it written as F, which to me makes a lot more sense, but for some reason in chemistry we like to use the number or the letter nu. All right, letter B. What does it mean for something to be quantized? Give 3 examples of things that are everyday things that are quantized. And stairs are quantized, so you can't use that as an example. Okay. So quantized just literally means you can count it in whole number integers. What does that mean? So if I have a ramp, let's kind of expand on this stairs example here. Okay. I can be like 1.5 way up the ramp, right? Or I can have 2.5 or 2 and 3/4 up the ramp. Right, this is a continuous spectrum. Okay, I can't say, this is one unit of ramp, 2 units of ramp, 3 units of ramp. There's no such thing. It's just one continuous thing. But when I get to stairs, I have 1 stair, 2 stair, 3 stair, or 4 stair. I can't have 1.5 stairs, right? Even if I put it here, we would just count this as another stair, just in a weird place, right? We wouldn't call it half a stair. Another example of things that are quantized are people, right? People are quantized. I can't have 2.5 people, right? No such thing. I can only have 2 people or 3 people. Now, you might be a jerk and say, okay, this guy's a half a person because he's mean or whatever, but you can't have physically a half a person, right? Even if they don't have legs or whatever it is, it's always just going to be one person. Another thing that's quantized is photons, okay, photons. Photons are, you could argue that it's an everyday thing because it's literally light, and light, you can't live every day without light. So that's also quantized, and let's see what else is quantized. We could say cars. You could argue that cars are, that you can have a half a car or whatever. But really, we only say there's only one. There's 3 cars there, or for 4 cars there, or you can't have really 4.5 cars. Just if you can, think of other things that you would consider to be quantized. And the most important thing to get out of this here is that photons are quantized. Photons, the radiant packet of radiant energy, those things are quantized. You can't have a half or a fraction of a photon. All right, number 2, complete the following table. If the wavelength is given, calculate the frequency of a photon that is of that wavelength, and vice versa. Then calculate the energy of 1,000 photons, and yada yada yada. Okay, let's do the electromagnetic range first. Okay, so they want us to look at the electromagnetic spectrum, find where these wavelengths fall. Okay, and really it's easiest if you would probably just go with the wavelength here. So let's look at the wavelengths. Okay, I'm at 200. Okay, 200. Here's times 10 to the 3. That's 1,000. And here's times 10 to the 0. That's 1. So 1 and 1,000. So it's going to fall somewhere within this range. So I'm going to call this radio. Okay, and you will be given something like this on the test. You don't have to memorize the spectrum, so please don't. Okay, number 2, we got 2 meters. And that's still between 1 and 1,000. So I'm going to put radio. Now I'm at 2 centimeters. Now I'm broken into the microwave region. And actually microwave, if you don't know, the reason we call a microwave, right, where we cook our food, is because water absorbs light in the microwave region. And so we call it a microwave, is all we're doing is shooting microwaves into it. And the water that's in our food and in our drinks, water is in at least some quantity in all of the food that we warm up. And so it'll warm up those water molecules, and the water will subsequently transfer that energy to your food so that it also heats up, okay? That's why we call it a microwave. All right, lastly, 2 millimeters. All right, so here's the millimeter region. This would technically be 1 millimeter, right? So this also falls in the microwave region, but if we're at 1, which happens to be in your homework, which is 1 millimeter, I would just say probably IR, but I'll just put IR somewhere between IR and microwave. It's a little ambiguous. Okay. Now we got to solve for frequency. Now the most important part of solving this problem, and in solving a lot of problems dealing with light, is knowing the equation of light. C is equal to lambda nu, okay? Where lambda is actually our wavelength, and nu is our frequency, okay? And if you do that, I got units of meters for wavelength and units of 1/seconds for frequency, or also known as hertz. 1 over seconds is the same as hertz, okay? Now, if you multiply these together, you get a meters per second, which makes sense because our speed of light is in meters per second, in units of meters per second. So I get 3 times 10 to the 8th meters per second. Okay, and that's equal to lambda nu. That's the equation of light. This is a constant, it never changes, so you never have to worry about that being a different number. Although you will see people use maybe like 2.998 times 10 to the 8th meters per second as opposed to 3. Either one is fine. For simplicity's sake and for this homework, I'll probably just be using 3. Okay, so algebraically, in order to solve for frequency, I have to divide lambda over, okay? And when I do that, let's see, what is my lambda? My lambda is 200 in this case, right? So I'm going to put 200 down here. And then what's that in meters? Okay, so my meters are going to cancel. Notice I end up with 1 over seconds. So when I do that, I actually get 1.5 times 10 to the 6th, and this is hertz, or 1 over seconds. I'm going to put that here, 1.5 times 10 to the 6th hertz. Okay, and it just so happens that for the rest of these, it's just off by by orders of magnitude. It's actually just going to be the same number, so 1.5, 1.5, 1.5, and then times 10 to the, it'll just be a different order of magnitude here because we're using the same numbers. So I'll just say it's 8 because this is 2 orders of magnitude in difference. Here's another 2 orders of magnitude, and then just 1 order of magnitude. So you can actually do that on your own, double check that these are right, but I'll let you know these are also, they're correct. You'll just need to know how to manipulate that equation, right? C is equal to lambda nu. If you have nu and you're solving for lambda, then you do the opposite of what we did. C over nu is equal to lambda, or C over lambda is equal to nu. Okay, so either one, you'll need to know how to use that so that you can solve for the other unit, okay? All right, now we're calculating energy, which is it's a different equation, okay? And we could use a part of the light equation, but I'll show you by how we don't have to, okay? So this is the equation for calculating energy, and this would be the energy of a single photon, okay? It's only a single photon. So the answer that we get out of plugging this in, is we're going to have to multiply by 1,000, okay? So when I multiply h nu together, that's going to be the energy of 1 photon in joules, and then I'll have to multiply that by 1,000 in order to get that for 1,000 photons, okay? All right, so h nu, what does that mean? So E is energy, but h is what we call Planck's constant, and you'll find that on your equation sheet. It's equal to 6.62 times 10 to the negative 34, really small number. Joules times seconds, joules times seconds, not joules per second. You'll see why we do that in a second. Okay, and in this case, we're multiplying it by 200, or by 1.5. Let's 1.5 times 10 to the 6th, and this is 1 over seconds, right? Look at that. My seconds cancel. Okay, they're on the opposite ends of the fraction. Okay, and I end up with joules, which is what I want because that's what energy is. So when I do that, I actually get 9.94 times 10 to the negative 28th joules. But this is for 1 photon per photon. So if I have 1,000 photons, and I know that 1 photon is equal to 9.94 times 10 to the negative 28 joules, then I get 9.94 times 10 to the negative 25 joules for 1,000 photons. Okay, 9.94 times 10 to the negative 25, that would be joules for 1,000 photons, okay? So don't make the mistake of putting it in for 1 photon, okay? This would have been your mistake if you put it in for 1 photon. Just make sure that you put it in for 1,000, okay? And also, these are, because we're using the same numbers here, relative, we're going to get the same number except just in different orders of magnitude. So I'm going to put 9.94, 9.94, 9.94. And then these are all be in joules. They're going to be some negative value. And actually, if you do this as wavelength, let's say if I multiply it by a number that's 2 orders of magnitude bigger, I should get a 2 orders of magnitude bigger. So negative 23. So this number is 2 orders of magnitude bigger. Same here, also going to be 21, but this is only 1, so that's going to be 20. I don't want to run through all those just because they're going to be the same number, and I feel like just learning this equation was all we were hoping for. So that's what you want to do. But one thing I do want to point out here with this trend is notice that when wavelength increases, right, this is going from 2 millimeters to 2 centimeters to 2 meters to 200 meters, what happens to my energy? My energy goes down, right, to negative, from negative 20 to negative 25. That's a smaller number. So energy and wavelength have an inverse relationship. If I have a long wavelength, then I have low energy. If I have a short wavelength, I have high energy. But with frequency, notice that when frequency increased, right, when from 6 to 8 to 10 to 11, my energy also increased, right? And that's another important trend. And the reason is if you look at the equation H nu, okay, it would make sense that if this increased, that energy also increased. If you were to solve for the same problem in terms of wavelength, okay, E is equal to H nu. If I know that C over lambda is equal to nu, right, solving for nu, I can plug this in here algebraically. E is equal to HC over lambda now. Now it's inversely proportional to energy, right? So if this increases, then energy decreases. So you can kind of see it algebraically too, that as one increases, like wavelength increases, energy decreases. Or if frequency increases, then energy increases, okay? So frequency and energy have a direct relationship. Wavelength and energy have an inverse relationship. Number 3, a typical microwave oven operates at 2.5 gigahertz. Calculate the wavelength of this electromagnetic radiation. How does this compare to the width of a typical microwave? The one in your house is about 30 centimeters wide, yada, yada, yada. Assuming the waves are standing waves, okay, how many nodes are in the microwave? Okay, we'll talk about nodes here in a second, but let's first calculate the wavelength of this electromagnetic radiation since we've just learned how to do that. So C is equal to lambda nu. I have what? That's frequency, right? So I'm going to say lambda is equal to C over nu. That's 3 times 10 to the 8th. Whoops, 3 times 10 to the 8th meters per second. Okay, and then you want to always leave this in regular hertz. Yes, it says giga, but you're going to want to put it in regular hertz, which is times 10 to the 9th, right? Times 10 to the 9th, 1 over seconds. And then my 1 over seconds will cancel. I'll be left with meters. And in this case, I get 0.12 meters. Now, we're actually dealing in terms of centimeters, so let's just move this over 2 places, turn it into 12 centimeters. Now, what is this? This is the value, the length of one wavelength. Let's clarify what a wavelength looks like. If I draw this, okay, which part of this is one wavelength? A lot of people, when they first learn about this, they think this is the wavelength. Okay, that's not one wavelength. That's actually what we call a half wavelength. The one wavelength would be one up and one down, just like this. This is one full wavelength. Okay, so this, in theory, is 12 centimeters for the microwave, like the microwaves that we're running through in our own microwave oven. Okay, so if I draw the microwave, I get a microwave here. Okay, and then if I draw, if I'm trying to figure out how that compares to the width of a typical microwave, what I can do is just take the length of the microwave, which we know is 30 centimeters, right? 30 centimeters. And then divide it by each wavelength. And if I divide it by a wavelength, it'll tell me how many wavelengths fit within that space, right? If I divide 30 by 12, it'll tell me how many wavelengths are there. So that's going to give me 2.5, and I'm going to just put lambda, 2.5 wavelengths. Now, what does that mean? That means when it's going across the microwave, it looks like this: 1, 2.5. Okay, whoops, that's kind of ugly. Let's see. 1. Oh, geez. Make a straight line here to help me out. 1, 2. Sorry about this. 1, 2.5. There we go. All right, so 1, 2, geez. 1, 2.5. All right. So this is what it would look like going across the microwave. But we know that microwaves don't just go and then end up wherever they're leaving. They actually bounce back. And so it'll actually bounce off this and become a standing wave because it's hitting the end of a half wavelength. And so this will end up turning into what we call a standing wave, because here I got another half wavelength coming back, and then 1, 2 more waves. Okay, 2 more wavelengths. And so this is what the wave looks like going there and coming back. And that's how we're comparing it to the width of a typical microwave. Now, assuming this is a standing wave, right? Standing wave is where we have 2 fixed ends of a wave, right? We're not ending at like this part of a wave. We're not ending right here. We're ending where this is the wave, right? We're not ending at the middle of a wave. We're ending at the node or at the beginning of another half wavelength, okay? So what does that mean? If I had 2.5 going this way, here's 1, 2.5, and then another 2.5. Okay, that's a total of 5 waves, 5 lambda. Now, when they're asking how many nodes are in the microwave, in a standing wave, okay, what do you see? A node And when I'm looking at a wave, the node is always where we're crossing zero. Okay, so if I have this, okay, this right here is not a node. That's not a node. Don't be tricked by that. A node is where you cross through zero, right here, right? This guy is crossing right through zero. This guy is touching zero. He's not crossing through it. Okay, when we start a wave, we actually start at zero, but we don't cross through it, and then we end up here, and we actually go right through zero. Okay, so that's a node. And so here, because we're not crossing through zero here, right here on these ends, those are not nodes. And so I'm going to circle all the other nodes, 1, 2, 3, 4. Okay, can you see those nodes right there? It's kind of messy, sorry about that, but hopefully you can kind of tell. Okay, there are 4 nodes. 4 nodes. Now this is important because when we start talking about the subatomic level, where we're talking about orbitals, when we have so many half wavelengths, in this case we have 5 wavelengths, right? You're always going to have n-1 nodes. n-1 nodes. That's going to be the rule. So if we're in the n equals 5 shell, we know we're going to have 4 nodes. And the same goes here. When we have 5 wavelengths here, we've got 4 nodes. Okay? Assuming it's a standing wave. Has to be a standing wave. If it's not a standing wave, it's not going to work. Okay? All right. On to number 4. The 4 centimeter band is a portion of the radio spectrum that is allocated to amateur radio and amateur satellite enthusiasts. What is the frequency of the electromagnetic radiation with a wavelength of 4 centimeters? And how does that compare to the 60? Okay, well, really all they're asking for is what's the frequency of that. So we know that C is equal to lambda nu. Okay, I have lambda, so I'm going to switch it over. C over lambda is equal to nu. It's equal to 3 times 10 to the 8th meters per second over 0.04 meters. Okay, don't make that mistake. Don't put 4 down here. It's 4 centimeters. We need to put this in meters so these meters cancel. I end up with 1 over seconds. Okay, and if I do that correctly, I get 7.5 times 10 to the 9th hertz. Now, how does that compare to the 60 hertz frequency of oscillations? Honestly, it's just gigantic, just so much bigger. So I don't know what else to say there. Just say it's way bigger. All right, like almost 10 orders, like 8 orders of magnitude bigger. All right, number 5. Prolonged exposure to UV radiation in tanning booths significantly increases the risk of skin cancer. What is the energy of a photon of UV light with a wavelength of 2.5 or 2.5 times 10 to the negative 7 meters? Okay, remember that energy can be calculated by h nu or hc over lambda, depending on the value that we have. In this case, we have meters of a wavelength, which is lambda. So let's use this equation here. So I'm going to say hc over lambda. That's equal to 6.626 times 10 to the negative 34. Joule times seconds, okay, times 3 times 10 to the 8th meters per second. My seconds will cancel. I end up with joule meters here. And then at the bottom here, I got 2.5 times 10 to the negative 7 meters. Okay, so meters will cancel. I'm going to end up with joules here. And when I do that correctly, I get, using sig figs, I get 8.0 times 10 to the negative 19th joules, okay? So that's how you'll solve for energy when you have wavelength, is using this equation. When dentists take x-rays, the patient is given a protective shield from excessive radiation. How much more energy is there per photon from a dental x-ray at this wavelength than from a UV radiation at this wavelength? Okay, so really all we have to do is find the value of each one. E is equal to hc over lambda for both. And honestly, just to save time, I've actually already solved these. But if you plug these into your calculator correctly, for x-ray, I'm just going to put x-ray here, 2.84 times 10 to the negative 15, and this is in joules, okay, versus 7.36 times 10 to the negative 19th joules for UV, okay? And if you divide this, and because they're asking how much more energy, we would just say this divided by 7.36 times 10 to the negative 19th joules. That gets us about 3,857 times bigger, right? Times, or not bigger per se, but more energy, times more energy. More energy. Okay, so I just used this equation to solve for each of these. I just plugged in the corresponding values for each one. Remember, when you're using picometers, this is going to be 70 times 10 to the negative 12th meters. Okay, that's what you'll want to use in your calculator. Here, you're going to want to say 270 times what? This is nano, times 10 to the negative 9th meters. Okay, don't put in 270 on its own, and don't put 70 in on its own. You will get the wrong answers. All right, letter C. Medical x-rays are often produced by slamming fast-moving electrons into a piece of tungsten metal and can have a wavelength as small as 21 picometers. Okay, 21 times 10 to the negative 12 meters. How much energy is in one of these X-ray photons? All right, same thing, E is equal to hc over lambda. I'm going to say 6.626 times 10 to the negative 34 joules times seconds, and then times, what, 3 times 10 to the 8th meters per second, that's light, divided by 21 times 10 to the negative 12th meters. Meters cancel, seconds cancel. I end up getting 9.47 times 10 to the negative 15 joules. Okay, square that. All right, takes about 4 electron volts. That's what this is. It's another unit of energy that we can convert into joules, which you'll see here. Okay, to break apart or severely damage DNA. Can UV light, dental x-rays, or medical x-rays damage your DNA? Well, really, let's see. 4 electron volts. Let's see if, let's calculate this in terms of joules and then compare the values that we've calculated here. Let's see, here and here and here, to see if they are bigger or smaller than this amount of electron volts here. So I'm going to say 1 EV is equal to 1.602 times 10 to the negative 22. This is in kilojoules, so it's not going to help too much. Let's put it into joules. I know that in 1 kilojoule there are 1,000 joules. Okay, so then if we do that correctly, we get 6.4 times 10 to the negative 19th joules. And that would be the minimum amount to severely damage DNA. So if I look at this value, so if each of these have at least a value of this or bigger, then they're gonna damage DNA. This number is for sure bigger, right? And this was what? X-rays. So yeah, X-rays will for sure. Let's look at UV rays. We calculated a UV here. 8 times 10 to the negative 19th. Yeah, that's bigger, right? That's going to severely damage DNA. Probably not as bad as X-rays, but it will damage it. And then let's see. Was there anything else? No, all these X-rays were a lot bigger. So I'm going to say just yes. Because, yeah, they'll all damage DNA. All of them. All right? So that is the first half of problem set 5, light. And I hope that was helpful.